has logged into WebAssign yet. I'm missing a couple. They will get an email from me, but I think everybody else is. So I think so far everything's working except for the McGraw-Hill stuff. And I know it's not working, and I'm not worrying about trying to get it working until after next week. So you're not behind on any of that. And then for you guys, I think when I talked to Mr. Grimm for you guys over in Tonkawa, when I talked to Mr. Grimm, he's going to probably go ahead and try to get as many labs done up front at the beginning of the semester as he possibly can. And I think I'm going to try to do the same thing over here. So we will end up probably doing labs prior to when we're lectured with them, so that we can get the 5 hands-on labs done for the ones of you that are attending in person. Right now I have 4 of you that I have to get a device for. Hi. Is it Raymond? Is that how you say your name? How do you say your name?
Yes, ma'am. Ramon?
Ramon, okay. More of the Latin side, okay. I need to make sure you get on the WebAssign, okay?
Okay.
Okay, yeah. Make sure you get on the website. So, so kind of giving you guys a heads up on that kind of stuff for the labs. But I know of 4 of you that I got to get a device for, and for the device people, we're not as pressed for time, so we'll get those worked out. All right. So I think we've actually are doing pretty good. Okay, so we're going to dive in. Maybe. We'll see how it works. Technology is great. And Hunter, you're going to have to speak up because of the way those stars are. Can everybody hear me? Because that was one of the issues we had earlier in one of these rooms.
Yes.
All right. Okay, so we got it. Okay, I'm going to shift things around so that I can make things work a little bit better. Okay, so on Wednesday, we actually started talking about simple harmonic motion. Well, today I've actually gone in and I've looked at the homework, and hopefully most of you have already gone through all the lovely Gorey theory, because there's Gorey theory associated with it. But I'm going to kind of remind you of a couple of things. Just as, because we've slept over the time, remember that we end up using triangles a lot. And we're going to end up using this right triangle concept to mean something a little different as we get into electricity. We still have our vector concept here, we still have our angles, and we still have our R and our X and our Y over our hypotenuse, our adjacent, and our opposite, whichever way we wanted to do it. And we have our good old Pythagorean theorem that a squared plus b squared is equal to c squared. And we've got that the sine of an angle is going to be y over r. Cosine of the angle is going to be x over r. And we could do this as x squared plus y squared is equal to r squared. So this is all stuff that we've worked with, we've dealt with it, and it kind of seems a little simplistic, but it's probably been a long time ago since you guys looked at trigonometric identities. So let's kind of look at this trigonometric identity real quick. I'm going to do this x squared r squared one. So I'm going to take my x squared divided by r squared plus y squared divided by r squared is equal to 1. And if I look at this is just x over r. Ooh, goody, that's cosine squared. And if I look at this one, this is just my sine squared. And that's all equal to 1. When you guys get into statics, and when you guys get into your engineering courses, while we've gotten used to the calculator and having the calculator always there, historically we didn't have a calculator and we would have to look up the sine of the angle or the cosine of the angle, or we'd have to use a slide rule to get there. So there are a lot of mathematical tricks that we're going to just use the ratios. because that's all sine and cosine are. They're just ratios. Okay? And so some of these mathematical tricks we use to get us a long way around. Now, the reason I bring that up is because if you've started your homework, which I actually looked at, and not so many of you started it yet, but if you look at it, you're going to need an identity that you probably haven't seen in a while. And I can write it like this. So if I have any angle A plus any angle B, this is going to give me cosine of A, cosine of B, minus sine of A, sine of B. And this becomes important because remember what we've seen so far is that my simple harmonic oscillator is going to be written the position of X or the position of Y. And if I'm doing my spring this way, I'm doing this and it's oscillating back and forth this way, I'm going to do it as X. Or I can do it as Y if I'm doing it up and down. It doesn't really matter. If I'm in one dimension, right, this is what we end up dealing with. I'm in one dimension, I can use X and Y and I can use them interchangeably. It's going to be some A, where that's the amplitude, cosine of my frequency, or my angular frequency, plus some phase angle. Okay? So I can use this, and I may have to use something like this in order to get through to the next, kind of the next statement. So just kind of a reminder there. I tried to go back and look in the algebra book as to where that one is. I didn't find it immediately, and I didn't find it in the calc book immediately. You know, because I just was kind of wanting to. Now, this stuff you'll find in the appendix, because this is our good old reminder. It's in the appendix of our text. And I even think this identity is in the appendix of our text. So just kind of as a refresher for why we had to do all of that lovely stuff. So let's start. Let's just kind of refresh what we're going to end up with. So if you've watched the video, and it seems like a lot of you have, we can relate our position versus time, whether that's in the X direction or the Y direction. We can relate it as the amplitude cosine of our angular frequency times the time plus whatever phase angle. And because we deal with that phase angle, if I go to another textbook, or if I go someplace else, this could easily be written as a sine function. But we're going to stay with the convention that it's cosine. When we do it in the lab, we're going to use the sine function just because I want you to see that it's the same thing. So we've got that set up. We know that if I do a velocity versus time, I'm going to take that first derivative, and that's going to give me the minus A omega sine omega t phi. And this is going to give me my velocity of my oscillator at any point throughout. And then, of course, we've got our acceleration versus time, which is just the first derivative of the velocity versus time, which is the second derivative of the position versus time. And that's going to give me my minus omega squared cosine omega t plus phi. And as we discussed on Wednesday, when I'm looking at it and I'm looking at my oscillation, so I'm going to do an up and down oscillation. If I look at the energy at the top, this is going to be potential energy. And because I'm dealing with the spring, we've got to kind of remember that I have a kx squared for returning it back and forth. Because that's what's going to be driving this. particularly if I'm using the horizontal, right? If I'm using this horizontal, there's my compressed one. This is the one at equilibrium. And this is the one that's stretched. Let me do the line. So I got my line there, got my line there, got my dash line. So this is my 0, and this becomes the amplitude, and this becomes minus the amplitude. And we can see the shift of the energy. And we know that at this point, the velocity is equal to 0. At this point, the velocity is equal to 0. And we know that the velocity max is here. But we also know that my stretch or compression, remember in this case, we end up using this x here. This is not this x. This x is actually compression or extension. So this relates back to the stretch of the spring. Okay, that relates back to the stretch of the spring. So this has a 0, which means that the potential energy is equal to 0 at that point. Here, we get the kinetic energy is equal to 0. The kinetic energy at this end is equal to 0. And in here, the kinetic energy is going to equal 1/2 mv squared. And just so that I don't get things really worked up, which I have been known to do. I didn't bring it in that shape. You can play with this, and you can bring in that the frequency, I believe it is the square root of k over m. And if I look at k is, let's just see it, let's use our unit analysis to make sure I did it right. K is in Newton meters. And mass is in kilograms. And Newton is in kilogram meters per second squared divided by meters. Meters cancel, kilograms cancel. I end up with 1/2 squared, and I'm in the right units. And that's how we get this relationship between the spring constant and the mass, is by doing this analysis. Okay. Now, let's look at something real quick. Hopefully somebody has a calculator handy. Okay? Because when we look at the simple pendulum, and normally I have everybody do this experiment. But I don't think, the way last semester went, the way last fall or spring went, I'm not 100% sure that the experiment got done. So this is in here just for reference. We'll go ahead and use a different color. And I got a pendulum here. And if I'm dealing with a simple pendulum, I've got my length, right? I've got my length. And I'm going to bring up to an angle. And we're going to release the pendulum, and we know what happens. It goes over and it comes back. And we can actually measure the period of the pendulum. We can actually get that period of the pendulum. And in our book, And in several places, and this is one of those things that you can go out and in the book and get through there. The period of a pendulum is approximately equal to, and I'm doing this on purpose, the square root of the length divided by gravity. Because we know at this end we've got potential energy, and that potential energy is going to equal mgh. And that's the height that it's up. We've got it that it'll come down here. We'll get at the bottom, we'll get our 1/2 mv squared. And we can use this back and forth. And the reason I've got this approximately equal thing in is that we've had to make a critical assumption in order to get this equation. Okay? We've had to make a critical assumption to get to this equation. Because a couple of things that are going on. So if I'm looking at it from a micro scale here, we know that this is actually the path of the pendulum. So this is S, or the distance traveled, that the path of the pendulum occurs. And if we've got our angle here, if we are at such a point that we've got this is small, this line right here is going to approximate a straight line, and this is going to be the sine of the angle to give us that side. Because we want it to be approaching the straight line. So somebody's got their calculator and they've got it in degrees, right? I want somebody to give me degrees. Give me the sine of 10 degrees. Somebody punch it in and give me the sine of 10 degrees.
.1736.
0.1736?
Yeah,
Are you in degrees?
should be. Yeah.
We have 0.1736. Give me the sine of 5 degrees.
.087.
0.087?
Yeah.
Are you sure?
That's what I got as well.
Okay, good. Okay. Let's do it in radians then. What's 5 degrees in radians?
Negative 0.959.
No, what's 5 degrees in radians? Convert degrees to radians. Can't be negative. 90 degrees is pi over 2.
It's going to be like pi over 18.
Okay, what is pi over 18?
I got that it was 0.0872.
Okay, 0.0872. Okay, that's exactly what I need to know. It's in radians. Okay, so 5 degrees is 0.0872, and the sine of 5 degrees is 0.087. Let's do it for 10 degrees, but we want the degrees in radians.
.174.
0.174, and the sine of 10 degrees is 0.173. Now let's do it for 20 degrees.
20 degrees in radians is 0.349.
0.349. Now give me the sine of 20 degrees.
.342.
0.342. All right, let's do 45 degrees. And 45 degrees is pi over 4. So I need that in radians, I need that in the number.
.785.
0.785. Now give me the sine of that.
.707.
0.707. Okay, so when we were at 5 degrees, and we did it in radians, we got 0.0872, and the sine of the angle was 0.872. When we got 10 degrees, it was 0.174, and this was 0.173. And when we got to 20 degrees, we get 0.349, and we get 0.342, and at 45 degrees, we got 0.785, and we get 0.707. So as long as I have a small angle, the angle is approximately equal to the sine of the angle. And this is called the small angle assumption. The other part when we're dealing with the simple pendulum is that we assume that the length is much, much greater than whatever angle that I end up dealing with. Okay? Because one of the things that happens is if I have a pendulum and I have a really long lever arm here, if I got a really long lever arm and I put it out at 45 degrees, I get dampening very, very quickly. So I'm also going to get a dampening problem if I have the arc of my pendulum is going really big. I'm going to have to worry about friction. I've got to worry about air resistance. But if even then I'm making the assumption that the length is very, very long compared to where my angle is going to be. So we call this the small angle assumption, and that small angle assumption leads to our period in our pendulum. And you guys will find out that this small angle assumption, we use it all the time. We're going to see it in the Young's double slit experiment. We're going to see it in a couple of other places when we get to optics. We're going to see it over and over again. Another reason why I like to start with simple harmonic motion, because we want to bring this back out to remind folks that we're going to use this small angle assumption. But once I get the period, of course, then I can relate that back to the angular frequency, because the angular frequency is going to be 2 pi times the frequency, which is also 2 pi over the period. So we can go back and forth between this. So I think one of the homework problems that you guys have to deal with was what happens to the period if I change gravity, and what happens to the period if I change length. And this, remember, is for a simple pendulum. And in the simple pendulum, we can act that this is a mass, and we assume the mass of the string is approximately 0. Or we assume that the mass of this down here is so much greater that this is going to act like 0. Okay, so a couple other reminders on that one, because you do have a couple of physical pendulum problems, homework problems. You do have a couple of them. I want to remind folks how you calculate the center of mass. So the center of mass, whether it's going to be in the x direction, y direction, or z direction, you're going to use that if I'm dealing with point particles. So this is point particles. And actually, we use this assumption to our advantage a lot. We knew that 1 over the mass, and this is the total mass. That's the total mass, is going to equal the sum, or 1 over the total mass, and then I take the individual particles and their x directions, and I'm going to sum that for all my particles. So remember what this looked like. And you may have gotten it in calculus, you may have gotten it in math somewhere along the way, you may have gotten, we did kind of do it in physics 1, but we did it in a real hurry. But if I have 3 particles here, and I want to find the center of mass, I'm going to do, and if this is 1 kilogram, and this is 2 kilograms, and this is 3 kilograms, we know that at least in the x direction, it's probably about halfway, right? Because we can do this intuitively. We know it's probably going to be about there. And we know it's going to be, if this is 3 kilograms and that's 2 kilograms, we know it's going to be somewhere over here. And remember that the center of mass does not necessarily have to be on the objects. Now, we can take this, and if we do it for the calculus right, if I'm doing a solid object, this just becomes an integral, and we're going to deal with the integration of it. The other part of this is if I'm doing rotation. Remember, we ended up saying, okay, I put these on things and I'm going to start spinning them around. The orientation of how I spin these things around also becomes important. And I can use that the moment of inertia is going to equal the sum of, if I'm doing individual particles, it looks like this. And you'll see it in your calculus book, you'll see it in a variety of other places, but if I did it over a rod, the good beauty of this is we intuitively, this is a solid rod made of the same material. We know exactly where the center of mass is, right? It's going to be along the axis down the middle. It's going to be halfway down. And because this is a circle, it's going to be there, and that's as long as I'm spinning it this way. Well, that's center of mass, but if I'm spinning it, it's going to have a different moment of inertia if I'm spinning it. But that means that for this rod, we know where the center of mass is, because that's where gravity is going to act. I can balance it. Remember, center of mass is where I can actually do the balancing act, if I can actually get my pen to balance. We intuitively know how to do that. And because we're going to be professional we're engineering students, or student engineers, we know that we have resources out there that says I can go look in my calculus book, in the back of my calculus book, and it's going to tell me that if I have a cone, the center of mass or the moment of inertia is going to be located there. And for those of you that have gotten your Fundamentals of Engineering handbook, there's pages of these for common objects. So we can go and look it up, you know, we can cheat, we can look it up. But that's where we got the parallel axis theorem, okay? So now if I have a rod and I'm going to do a pendulum, okay? We know that the center of mass is going to act through that spot. If I lengthen the rod, all I got to do is do the I is equal to I center of mass plus whatever the new location was. And that's the parallel axis theorem. Okay, and the good news for all of you, you are not going to see a physical pendulum on any test or quiz. You do have 2 physical pendulum homework problems, because I'm making sure that you guys have an opportunity to see it, but we're not going to spend time on that one. They're fun and cool and all that, but you're going to get that over again. You're going to get this material again in statics. because we're going to look at it in equilibrium. And we're really going to play with the physical pendulum when we get to dynamics. And if you go the physics route, it's in mechanics and advanced mechanics is where you're going to get it. So I'm just introducing it to you guys at this point. All right, but that hopefully will help you kind of go and refresh your memory about where some of the stuff is when you get to that physical pendulum. All right, so let's play. So just to keep us all on the same page, I'm going to rewrite the equations here so we have them, and we have them easily accessible. Those are our three equations. So, I'm going to give you a curve, and I'm going to tell you something about this curve. We can look at it and say, yay, it's a sine wave, or cosine wave. I'm going to tell you, and I'm actually drawing that this is the amplitude, and I'm going to tell you that the amplitude is equal to 6. That could be 6 centimeters, it could be 6 meters, and I'm just going to tell you that that amplitude is 6. I'm going to give you that the period of this cycle, we'll go ahead and call this 6 meters, just to make life easier for us. I'm going to tell you that the period is 8 seconds. And I'm going to, because I didn't give you any context, I'm going to tell you that the phase angle for this one is 3 pi over 2. I want you to write the wave equation.
You want the position, or do you want the velocity or the acceleration?
Well, start with position. That's the wave equation. Position, just give me the position. Because if I get the position, and I get the position right, hopefully that means you can get the other two right, right? Oh, I gotta get to the next one. I'll give you a couple more minutes because I gotta get to the next one so that you can get the homework done. Everybody think they got it? X of t is going to equal 6 cosine, and I'm going to do it so you guys can all see it, 2 pi over 8t plus 3 pi over 2, and you can simplify that down as pi over 4 t plus 3 pi over 2. And then, of course, you can plug it into the other two. All right. I'm going to give you an equation. X of t is equal to 3 cosine 3 pi t minus 8 sine 3 pi t. And this is an equation for a simple harmonic motion or simple harmonic oscillator. It's your equation there. We want to find the amplitude. We want to find the angular frequency. And we want to find the phase angle. And if you haven't done this in a while, and you haven't played with it in a while, you're going to look at this and you go, okay, I know I can do that, but I'm not quite sure how. So let's go and remind ourselves that cosine of A plus B is going to equal cosine A cosine B minus sine A sine B. And because these have the same, we could go, oh, phew, my omega is going to be 3 pi. I can just go ahead and take that right out. Because I'm going to actually do that this is cosine omega t plus my phase angle, which means I get cosine omega t cosine my phase angle minus sine omega t sine of my phase angle. And this looks an awful lot alike. I can use this form to get me where I need to go. Okay? I can use this form to get me where I need to go, in that this now becomes my amplitude cosine omega t cosine my phase angle. And that's going to equal 3 cosine 3 pi t. So A cosine phi is going to be 3. I do the same thing for this end, and I get A sine phi is equal to 8. I'm going to use another trig identity to help me out. I'm going to use the cosine squared of the angle plus the sine squared of the angle is equal to 1. So I'm going to end up with that the amplitude squared is just going to be 3 squared plus 8 squared. So the amplitude will end up being the square root of, it's 64, square root of that is going to be the square root of 73. And then to get phi, the tangent of phi is going to, phi, not theta, the tangent of phi is just going to be the sine, I get a sine over a cosine, and that's going to give me my 8 divided by my 3, and then I can solve for phi, and if I do that, it's approximately 69 degrees. But again, since we've had an interesting year, so that math is a little rusty. Okay, questions? Is this making a little more sense?
Can you go back to the previous page for the wave equation?
This one?
Yeah.
That one right there?
Oh, yeah. Go back up a little bit. I think it's gonna try it out.
Okay, let me roll it back up.
There we go.
Where we go?
What?
Where did we get the 2 pi over 8 in that wave equation?
This 2 pi over 8?
Yeah, that one.
Well, remember that omega is equal to 2 pi times the frequency, or 2 pi over the period, and I gave you the period was 8. Yeah, omega is going to be 2 pi times the frequency, or it'll equal 2 pi over the period. I gave you the frequency, or the period was 8 seconds. So all I did was plug in the 8 right there.
Okay.
Other questions? Coolio. So Monday, we'll start chapter 17. Because then we'll start putting this in terms of position and time. Traveling pulses. So we can keep rocking on. Don't forget you've got some Pivot Interactive stuff that's due. I will warn you guys that the way things have happened this year, so just kind of give you a heads up. After this class, unless I have somebody that's hanging around or needs me for something, I will be headed back on the road, back home. And I'm not likely to answer emails for the rest of the day. Now, because of the way things are going, I'm usually on my computer over the weekend. So I'm hoping that I can respond, but I'm not going to respond as quickly as I normally do during the week. And I will tell you that after this last week, my odds of responding to something in the evening is probably slim and none. Because of the way things are happening, it's been kind of a little bit chaotic. So, and I anticipate that we're going to have some of that. I will encourage you all to have safe behavior over the weekend. Because I'm anxious to see what certain things that are happening in the state this weekend, I'm anxious to see the results of. But just caution, use caution. Stay socially distant and stay safe. Any other questions? Everybody else good?